Alright everyone, hello all. So today I'm going to be walking through Project 1 and going over the multi-threading and inter-process communication experiment. For this one, I set up a virtual machine using VirtualBox, using a Fedora virtual machine and coding in C++. The reason I picked those is VirtualBox seemed the most flexible. Fedora, I'd heard of that one before. It seemed to be very robust and people had a lot of good things to say, so I was curious to try it. And then with C++, I've never gotten to code C++, code in C++ for a programming assignment, so I thought this would be a great opportunity to sort of take on an extra challenge and try out a programming language I haven't used before. Alright, so I'll go ahead and pull up Visual Studio Code and sort of start here. Alright, so let's talk about concurrency. So when we're talking about concurrency, we're essentially talking about making things happen at the same time. In this project, the goal is to achieve this using threads. They act as mini processes within the main program. So in this case, the way that I sort of started by setting it up was sort of bringing in the basic libraries for that. So thread, IOStream, the usual ones, and created a random sleep time, chef methods. So in this case, for my project, I went off of a kitchen theme, so I made the chef methods and sort of got their information set up, and then created the chef threads, and then finally used .join. So this is the multi-threads portion of the experiment. So this was the beginning. This is just a basic creation, basic creating threads and showing concurrency as sort of the base for eventually creating code that uses these same chefs and these same principles to demonstrate deadlock and then eventually deadlock resolution. So creating threads is actually quite simple. So I just use std thread and gave it the function I want to run in that thread, and then in this case it was my chef functions. Sleep would sort of act as their cooking function, and then when they're ready, it'll just say their dish is ready. All right. Alright, so when the code is run, as you can see, there are 10 chef outputs, so each one says it's ready, it sends it out, so basically representing the 10 chefs running concurrently. So I also used .join. .join is a synchronization mechanism. It is used to tell the main thread to wait for specific threads to finish its execution before proceeding, to guarantee that all 10 chef threads are able to complete before the main method, the main thread continues. But this is where things get interesting. So like I said, this is just sort of the basic demonstration of threads and concurrency. But what happens when there's shared resources? So for example, in a kitchen, chefs often have to share resources. So in this case, what if the chefs have to share ovens or stoves? So that's where things can get interesting. Alright, without proper coordination, having threads compete over shared resources can lead to what's called a race condition, where the final result is unpredictable and depends on which thread finishes first. To avoid this chaos, we use mutexes. So here I have the stove mutex and the oven mutex to represent the shared resources that the chef functions will use. And like I said, it's the same threads, so it's the same head chef, sous chef, same resources. It's just a bit more robust to demonstrate deadlock. So what this part represents is that mutexes can be a double-edged sword. If not used carefully, they can lead to a deadlock situation. So two threads, each holding one mutex, waiting for the other to release theirs. So in this case, the stove is locked and the oven is locked, or the oven is locked and the stove is locked. So when the chef function is called and moving through, so each one has the name, the dish, and then is the stove locked or not. So in this case, if the stove is locked, then the oven is locked. If the stove is not locked, then it ends up locked anyway. So the idea here is that they're always going to be in a state of waiting for the oven or the stove to be unlocked, and it's never going to happen. So if I go to run this code, so as you can see, unlike the multi-thread program where all of them were able to run successfully, this time only trainee chef and head chef are able to run because the oven and the stove lock, and now the rest of the program is just waiting indefinitely for those two threads to release those resources. Luckily, there's ways to prevent and resolve deadlocks. One effective technique is to use locks to allow multiple mutexes to work simultaneously and prevent a hold and wait situation. Another approach is to enforce a strict order in which threads can acquire mutexes to ensure that they don't get into a deadlock in the first place, which sort of gets into deadlock avoidance, and if that's even possible. And that's where it gets to the bulk of it. So taking this code, it can be applied here, which is the resolution code. So this has the same code for the deadlock, but with some resolutions or with a solution put into place. So it still has the stove and oven mutex. This one has a fancier way to generate a random number for sleep. But the core principle here is that the most crucial aspect of this code's deadlock prevention is it has a consistent lock ordering. Every chef function acquires locks in the same sequence, stove then oven. And this matters because deadlock occurs when multiple threads are waiting for each other to release locks. If threads acquire locks in different orders, a circular wait condition can come out of that. By eliminating the possibility of that circular wait, we're able to sort of just avoid deadlock altogether. So that's one of the most important parts of this is stove and oven have a particular order. But there's another part of it here, which is just safer practices with the mutexes. So mutexes are used in safe practices. And it's a standard C++ synchronization tool. So mutexes provide exclusive access to shared resources, ensuring that only one thread can hold the lock at a time. It prevents data races and other concurrency issues. Lock and unlocking the code using mutex.lock or mutex.unlock. So this is kind of just that's the standard way to use mutexes. So then in the chef function, so for example, with the main function, it uses thread.join to wait for each chef thread to finish before exiting the program to prevent the program from terminating prematurely and potentially leaving threads in an inconsistent state. And then something else to sort of point out is in the chef function for this one, I also incorporated try-catch blocks, so exception handling to handle more obscure cases, which is just always a good practice to prevent a program from crashing if unexpected errors occur. Something else that helps is the random sleep time. So like I said, this one has a bit more of a fancier random sleep time, because it simulates, one, it's interesting because it simulates realistic kitchen activities, because in a real life kitchen, things kind of move at the pace that they're able to move. But it also helps to expose potential race conditions and other concurrency issues that might not be apparent with fixed delays. The code provides here provides clear output messages that indicate which chef is using which resource, which I can demonstrate now. So in this case, something that's different is this one also has more print statements involved, just to sort of show where each thread is when the code is running. So this one takes a little bit longer. So this one has the clear output to provide messages to indicate which chef is using which resource, which can be helpful to demonstrate the program's behavior. Alright, so basically just in summary, this code effectively prevents deadlock by consistently ordering lock acquisitions and employs safe practices through mutex usage, exception handling, and proper thread management. So that sort of covers the multi-threading side of the project. So let's zoom out and consider communication between different processes. This is where pipes come in. So just one more, right here you can see all of the chefs were able to go through their orders and sort of use the stove and the oven to finish their tasks. Alright, so like I said, zooming out to consider communication between different processes, this is where pipes come in. So a pipe, in this case, can serve as a one-way communication channel between processes, like a message tube. I use the pipe function to create this channel and then use fork to create child processes. So in this case, here's a pipe with a child, and then there's a second pipe with a second child. And just to sort of stay on theme with the kitchen, one of the messages is from a waitress and the other is from a customer. So in my example, I have the waitress process sending a message to a customer process, and the waitress asks for the order, and then the customer it simulates a response. I use the pipe function to create this channel, and then fork to create the child processes in order to demonstrate the pipes writing messages, or the children writing messages to the parents via the pipes. Alright, so this one, pretty simple output. The waitress, what would you like to order? And then the customer. So what's going on here is the children are sending these messages up to the parents via pipes, and so the pipe was able to read these messages and then display waitress, customer, and a little simulation of an order. Okay, so to recap, just basically this has been exploring concurrency, C++, multi-threading, deadlocks, inter-process communication, pipes, and a lot of the essential tools for building complex and efficient applications that can take advantage of modern multi-core processors. Understanding these concepts is crucial for software developers because it allows them to create responsive and high-performance applications that can handle multiple tasks concurrently. And that's all I've got for today, so just thank you so much for watching my video and looking at my code demonstrations. I look forward to the future projects.